Okay, here we go.
I don't get it.
All right, so I want to start off. We gotta just before we jump into this, the key, the big secret, how the reason people are successful in life, and this isn't about anything you do. The reason people are successful is because they can become invested in a process. If you want to be a good basketball player, what do you have to do?
Practice.
You have to put in a lot of time. Okay, but in order to put in a lot of time, what probably has to be your feeling about the game of basketball?
Dedication.
You gotta like it. You gotta like it enough to be to a point where you can find things about it interesting enough that you're willing to spend the time doing those things, even though those things may not in and of themselves be really interesting. Same thing with snowboarding or whatever you want to choose. The skiing, all right, whatever you want to be good at. Those are things that you can generate some interest in, right? And so the secret to success in life, and I really believe this. I mean, there are some really key things you can do. And I'm not going to spend too much time on it today, but I think the big one is this: if you can become interested in things that you're doing, then you're going to be good at them, right? And so you have to, in order to do that, you have to be kind of an interesting person. Really, you do. Interesting people are people who are interested in other things, and it's about a direct correlation. You are interesting insofar as you are interested. And so what you don't want to do is allow yourself to fall into the trap, and I think this is easy to do in our culture, of being, just blasé about stuff, not being interested. Later in life, I promise you, the things that make you interesting to other people are not the same as they are in high school. They're very, very different. And in order to become the kind of person who is going to be able to enjoy interesting relationships and have an interesting life, you sometimes have to fight through the wall of ambivalence that you see in a high school culture, right? And so just challenge yourself to do that. I mean, seriously, it's not easy to do. I mean, sometimes it's hard. I'm not interested in everything. I was never interested in everything that I was exposed to. But I found very quickly in college, when I was in a very competitive college, that I had to. And so my deal was, if I went to a class, I was going to say, okay, this guy is, when I was in college, the professors that taught at my school, they were smart. So I was able to say, this guy is smart. He's got something to offer me that I've got to be able to, if I try hard enough, this guy is going to have something that he's going to be able to give me that's going to be of some value. And it may have been a class in a subject, like I'm not particularly fond of social sciences. That's not my thing. But every class I took in social sciences ended up being pretty good. In fact, one of the best classes I took was an elective class in anthropology. And it ended up, I would have never thought I was going to do that. But when I gave it a little bit of a chance, it ended up being a really interesting thing. And so you kind of have to allow yourself to do that. You have to embrace your inner geek just a little bit in life. And you can do it kind of secretly, but you got to do that. You got to have some interest, and you got to pursue those. One of them, I hope, is, and this is one that I know, I recognize that math is kind of an odd bird. Math is something where there's a lot of anxiety built into math. If you look, in our country especially, if you look at the number of people that have clinical math anxiety, people that just the thought of math makes them just, really nervous, it's quite a bit. And I think I know why. I think part of it's because they're never exposed to it in a way that's really positive. But math is nothing more than a language. It's just a logical way of connecting things. And the more you know about it, the easier it gets and the more interesting it gets. And so, I'm going to give you 1,001 facts this year about why it's important for you professionally, for example. Why it's a big deal, why learning math has the potential to be very rewarding to you professionally and financially in the future. And it's the truth, it really does. But let's just ignore that stuff for a moment and just think about the fact that it really is intrinsically pretty interesting stuff. In fact, there's some this is a weird concept that I'll just throw at you here. But math is the very smartest people in the world are physicists, people that study, that have gone through the rigors of learning the math and the analytical tools to do physics. I mean, there's only less than 10 people, it's estimated, in the world have the intellectual capacity to understand string theory, the topological math associated with string theory. And I'm not one of them, I promise you. And it's, I mean, there's a handful of those people that are just, their intellect is like ridiculous. I mean, the things they can do internally, intellectually are just phenomenal. But these guys that study this kind of stuff, cosmology and, they study the universe on a large scale, things like, cosmology and multiverse theory and things like that. These guys have started to question something that's really, really emerging as being very bizarre to them. And that is that math works as well as it does. It shouldn't. Math shouldn't be as descriptive as it is. It turns out that anything can be quantified mathematically. That's weird. It shouldn't be that way. There should be some things that are in our universe that are random and disassociated with math, but we haven't found it. Anything can be quantified. And these guys have started to ask the question now, why would that be? Because that doesn't seem normal. That's not what we would have predicted, the way that these guys think things should be. And so as a model for that, I want you just to think about something for a moment. Let's think about something maybe not as complex. Just imagine like a video game. Let's say that you are a character, and video games are pretty sophisticated, right? Imagine you're a character in a video game, in that universe. And the video game is sophisticated enough that you actually have developed the capacity to reason and to recognize yourself as being an independent character in the game, and et cetera, et cetera. Really sophisticated video game. In this video game, if you become a thinking, self-aware individual and you want to study the universe of your video game, if you're smart enough and you study it for a long enough period of time and maybe pass on this information to successive generations of video game characters, what are you going to figure out about the video game eventually? What do you think? In what way? Oh, okay, yeah. If you want to figure out the laws of nature in your video game universe and you study it enough, and you look for patterns and you develop a video game mathematics, what are you probably eventually going to uncover? Codes. Yeah, you're going to see that everything is mathematical, right? Everything is predictable once you understand the math that's embedded in the code, right, for the video game. And the people that code video games, it's just like, the code would just look like code, right? It's just going to look like, does anybody here do any coding? If you've ever done any coding or you do some coding, it is essentially math. That's all it is, right? It's just math. It's a system of rules that you follow, if-then statements. It's just math. But all of the physics that they would uncover would just be the math that's embedded in the code that was written to build the video game, right? Okay, so what do you suppose these physicists are starting to wonder about?
If we're cubes.
Yeah, they're starting to wonder if, they're not suggesting that it's likely that we are, but they're starting to wonder, they're finding it hard to rule it out. And one thing physicists do is they say, okay, could the universe be this way? How can we rule that out? No, it can't because of this and this and this. So that's off the table. But one thing they've been unable to take off the table is the idea that we're living in a coded sim. And how would you know if you're not? Pretty bizarre. I mean, how would you know? How would you know? Because it could be, and they even talk about it in these terms, it could be a sim of two different types. It could be an individual sim where you're the only person, and like me saying this, I'm just a character in your sim. That's one possibility, that there's only one person out there actually hearing this right now, and that person would be you. And you meaning the person that's hearing it. Everybody else is just a player in this sim, right? Then the other way, isn't that weird? Right? And then the other kind would be a sim where it's a parallel sim where there's a lot of independent avatars living in the same sim that each have their own, right? And I'm not saying I don't think this is the way it is, neither do they. But they can't rule it out yet. And so they're actually trying to design physics experiments and ways of testing this to see if this is possible. If they could literally find some glitches in the sim, and how would those glitches manifest physically? If they could predict what the glitches would have to be, you could go look for them. Pretty bizarre, right? Yeah. So, yeah, weird, right? But, I mean, we've evolved intellectually to a point where we can start to think about stuff like this, right? But I just want to point out, and I'm not trying to, I'm not, like I said, I don't believe this is the way it I really don't. I think it's very unlikely, and I think all those physicists would say that too. But it is pretty weird and pretty impressive how just completely math describes everything. It's hard to look at anything. Like look at the shapes of animals, for example. Let's just take a second and let's think about animals. Let's think about animals that vary by the places in which they live. Think about animals that live in extreme habitats. Think about animals that live, warm-blooded animals that live in very warm climates compared to animals that live in very cold climates. Animals that live in very cold climates, and like probably the most extreme cold climates would be in very cold water, right? So animals that live like in the Arctic and Antarctic waters. What do warm-blooded mammals always look like that live in those places? Okay, a lot of hair, and the hair has evolved to have little air pockets in it, that's true. What about their shapes?
They have a head.
Okay, they're going to be, if you think about the shape of these animals, they're all kind of spherical, right? I mean, they're, right? Seals, sea lions, whales, you see what I'm talking about, right? Even land animals, you look at things like bears, right? They're big and they're fairly spherical looking, right? Now compare that to animals that live in very, very hot climates. The animals that live in very hot climates are the exact opposite. When you think about like the hottest places on earth, the deserts, gazelles, giraffes, kangaroos, right? And some of these like kangaroos, and you might say elephants, but elephants are cheating because they have passive radiators in their ears. So they don't have to have as much of that pointy shape. But all the animals that don't have some trick for liberating heat into the environment, they all are kind of angular and long. And what's the reason for that, you suppose? Okay, it has to do with surface area. It turns out it's all math. If you want to live in a very cold environment, you have to come up with a body design that's going to minimize the amount of surface area relative to your volume, right? Because you have to retain all your internal heat. So what shape two-dimensionally, let's just think two dimensions for a second. What shape two-dimensionally has the smallest perimeter where you get the most bang for your buck, the most perimeter for the smallest area? It's a circle, right? Three-dimensionally then, what's going to be the shape that has the least surface area for the most volume? A sphere, right? Okay, makes sense, doesn't it? Right? Okay, you can look at things in those terms. I mean, if you had to design a video game that was going to be consistent, you would want to have some kind of a body design where animals that needed to be in very cold environments, there would have to be a set of restrictions mathematically on the kinds of shapes that they could have, right? Okay, circles, it turns out, are pretty interesting because they show up all the time. Circles are all over the place. You look at most of the matter in the universe is somehow contained in some type of a spherical container, right? A lot of times it's because of gravity. I mean, if you think about like stars have to be spherical because they're gravitationally compressed into that shape. The Earth is pretty spherical. Right, it's not exactly, it's an oblate sphere. It's a little bit bigger at the equator than it is at the, and that's because it spins. But it's otherwise, it's pretty darn spherical, right? Does it seem bumpy to you? A little bit? You look around, you see some bumps, we call them mountains. But let's think of an object here that's really smooth and spherical, like a billiard ball, right? Would everybody agree a billiard ball is a pretty good example of a sphere? This guy's shiny, it's smooth, right? Okay, what do you think if you look at the size of the bumps on a billiard ball in comparison to its radius, in comparison to its size? How do you think they compared the size of the bumps, mountains, on Earth compared to its size? Turns out that they're a lot bigger. The Earth is much, much smoother than a billiard ball. The mountains on an Earth are much, much smaller proportionally than the little imperfections in the paint on a billiard ball. So the Earth is pretty darn spherical, right? Okay, so maybe these circles, if we want to start talking about the universe, a good place to start. Okay, so a good place to start might just be with something easier like circles, right? But the thing about math is, a lot of times the way you build math up is you start with something relatively simple, and then you can just expand your knowledge to make it a little more complex. Like, for example, if we wanted to learn about spheres, we would just learn about circles and then tweak it a little bit, because it's basically the same, right? There's just a few key differences, but the math is very, very similar. So let's look here, let's look at circles, and what our goal is, and then really, today is just, it's a short day, I just kind of want to get this to a point where we can take an idea of a circle and turn this into a mathematical concept. And this is kind of important. What we want to do in math is we want to come up with a way to describe the set of all the points contained in a circle. Now, how many points are there in a circle? A lot, and by a lot you probably mean infinite. Yeah, there's an infinite number of points contained in the circle, right? So we've got to come up with a way of describing the configuration or the distribution of those points. How is that? What is it about a circle shape that might allow us to come up with a description?
Round.
Okay, it's round. Now, round, we're getting someplace, right? Round, but round is a word.
No,
Yeah.
3D.
What we want to do is 3D. Well, actually, it's 2D. Circle's 2D. Okay.
No one beers.
Oh, you said so.
All right. So, hey, I need you with me. We've got a short period. Stick with me, please. I'll have you raise hands if you want to, and I want you to contribute, but I'm going to have you maybe just raise hands to do that. Okay, so we want to get from a place where we're saying things like round, which is kind of a non-math word, to a description that's very mathematical. If I had more time, I would do this. Sometime we will, but I've done this with my classes in the past. Remember the game Telephone from grade school? So if you start with something with some expression on this, some phrase on this side of the room, and it goes all the way around to this side, what invariably happens to it? It gets totally messed up, right? It gets changed completely. However, what do you think happens if instead of saying a phrase, we say something like x squared plus 4 or x squared plus y equals 5? Do you think that changes very much? It doesn't change very much. How come? Say it again? Because they're simpler words. I mean, kind of. In a way they are. By simpler, I guess you could say by simpler, where you guys at? Oh, that's right. By simpler, I guess we could say that they're less colorful, right? The math words really don't have, if we say other language, it has lots of different meanings, because so much of what we do in life is communicate. There is a vastly disproportionate volume of your brain is devoted to simply communicating with people. I mean, you can say things like, nice job, and that could mean a ton of different things just based on your inflection, right? It might mean, yeah, I'm complimenting you, nice job. I might be being sarcastic, saying, that's terrible, right? So there's a lot of other stuff that goes with that, but not in math. You can't really add a lot of colorful connotations to y equals x squared. Y equals x squared. Y equals x squared. Same thing. Doesn't make any difference, right? It's a very simple, concise expression that means one thing, and that's the job of math, is to be unambiguous. It's not the job of language. The job of language is to be colorful and to be expressive, right? Because we're emotional beings. We're social and emotional beings. But in math, we want to kind of get rid of that in a way. We want to just be able to write stuff like in a contract where there's no way to dispute it. It's unambiguous, it's precise, it's exact, right? So we got to come up with some better ways than saying it's round. Let's think about a circle now. Is there any one particular point in a circle that might be interesting and important? The center, yeah. Okay, let's talk about the center. Maybe we could talk about the circle in relation to its center. What has to be true, maybe, of all the points on the periphery of the circle compared to the center?
They have to be the same length apart.
Okay, they have to be the same length apart, right? So maybe we could say something like this then. A circle is a set, and I'm going to even give you a special name for that. In math, the kind of name that we call a set like this is a locus. A locus in math just means a set of points in this case, a set of points that are going to follow a specific set of rules, right? There's going to be some specific criteria, or there are going to be some restrictions right? On where these points can be. So there's an infinite set of points in a circle, but it's the set of points that are all equidistant from a common center, right? And if I do that, if I take, like, for example, let's take this is one representative point, but if I drag it around so it always stays the same distance from A, which is at the center, look what I get. I get a whole bunch of points. That's not an infinite set of points, but we start to see it's a lot of points, right? We start to see that, yeah, that's a circle, right? Those points all fall within this manifold of points called a circle, right? And so that's so far so good. That's a pretty good description. Mathematically, to say a circle is the locus of points equidistant from a center. Now, the next step is for us to build a mathematical model that fits that, which is even better. Right? We want to write it as an equation, right? And so that's where we're going to just kind of start that discussion. I don't think we're going to finish it today, but let's see if we can at least think about, what that might look like. Okay, so what about this? So we said our circle is the locus of points equidistant from a center. Let's just take a random center. And we don't want to be specific. We want to pick a point that could be anywhere. We don't want to pick like the origin, because then whatever we do depends on the center being at the origin. We don't want that. We want the center to be any place in the xy plane for this circle, right? So we'll give it the coordinates. We'll call it point C, and we'll give it the coordinates hk, where h and k could be any numbers, no restrictions, right? Any real numbers. And then let's just say that the radius of our circle is going to be r. Or we're going to say radius, in fact, is the definition of that distance we were talking about, right? The distance between all the points on the circle in the center, we're going to call that the radius, give it a name, and we'll label it as r. So think about then, this is like a wire hoop, and here's a bead that we've labeled P, and I can slide this bead around the wire any place, right? The center is fixed, right? The center, once we set the center down for our circle, like we put the tack in the board or something, then it's fixed. We've specified a value of h and k, values for h and k. But wouldn't you agree that the coordinates of the point P of this bead can vary, right? There's an infinite number of possible values for x and y, but they're going to be tightly controlled because they have to stay, the bead can only slide on that hoop, right? So I can't just choose any value of x and y. I can only choose values of x and y that are going to work for the circle. We don't know how that's going to be yet. That's going to be the equation that we develop, right? But these have to be variables, okay? Well, one way that we could show this is let's pick a third point. Let's pick a point A that's lined up horizontally with the center and vertically with the bead, okay? So if it's lined up horizontally with the center, that would mean that the y coordinates would be the same, right? They're both k. Everybody agree? If it's lined up vertically with the bead, then their x coordinates would have to be the same. Does that make sense? Everybody, you gotta think about that a little bit. Does that make sense? That if points are lined up vertically, they must have the same x coordinate, and if points are lined up vertically, they'd have to have the same y coordinate, right?
You said vertically twice.
Say it again?
You said vertically twice.
Oh, I did, whoops. If they're lined up horizontally, they'd have to have the same y coordinates, and if they're lined up vertically, they'd have to have the same x coordinates. There, that's better. Okay, so then what kind of triangle are we making? If we're making A and C line up horizontally and P and A line up vertically. Ah, that's a right triangle, isn't it? Right? That's a right triangle because horizontal and vertical segments are perpendicular to each other, right? Okay, now we know something about right triangles. Right? We know for right triangles that if for example, if I have this right triangle where one leg has length A, one has length B, and the hypotenuse has length C, what's always the relationship between those side lengths? Say it again. A plus B doesn't equal C. It's more, but there is something that's always true. Remember from geometry? What? A squared plus B squared equals C squared, Pythagorean theorem, right? So we know in this case that A squared plus B squared equals C squared. So for our situation up here, it's not A and B and C. We could call this length CA, right? That means the length between the points C and A, the distance of that segment or that length. So we could say something like CA squared plus PA, that stands for a distance between points P and A. PA squared equals CP squared, right? Everybody agree? So all we gotta do then is just find names for CA and PA and CP mathematically, and that really would be the equation of our circle, because that's what has to be true, doesn't it? Right? So what is CA? Look at these coordinates. If the y coordinates are the same, then the distance between C and A is really just a change in the x values, because the y values didn't change, right? Everybody agree? So how would I find that? Let's just say hypothetically that the x value for point C was 3 and the x value for point A was 7. How far apart would they be? 4. How'd you get that? You subtracted. 7 minus 3. Good. Well, they're not 7 and 3. They're x and h. So instead of subtracting 3 from 7, we're subtracting what? H from x. Yeah. So CA is really just x minus h, right? Now, what about PA? The x coordinates are the same, so all of that distance is just the vertical difference, right? Just the change in the y coordinates. So if we're going from k to y, just like we went from h to x, what's that distance going to be? What's it again? Y minus k. Yeah. And CP, well, we defined that as r, didn't we? That's the radius. So then if we put all that together, look what we get. We just get the equation of a circle. X minus h is CA, so the quantity x minus h squared plus the quantity y minus k squared equals r squared. That's it. If we specify an h and a k and an r, that's going to give us the equation for any circle, right? In a mathematical way that is completely unambiguous, right? All right.
I feel like it